Hello, everyone, and welcome to the third hottest of winter or spring 2020, I believe. And it's my great pleasure to introduce my friend and collaborator, Karol Szumiło. I think we've known each other for 14 or 15 years at this point. We've written multiple papers, so I'm really, really happy to have Karol finally give a hottest. And his topic today is the constructive Kan-Quillen model structure. So Karol, please take it away.
Thank you. Well, first of all, thanks to Dan and to Chris for organizing and for inviting me to speak. So I will tell you about this constructive Kan-Quillen model structure today. And let me just say up front, there's not going to be homotopy type theory in this talk. The topic and this work is motivated by homotopy type theory, and it is being applied to problems in homotopy type theory. I will mention these problems and I will send you to some references, but there will be no type theory in the talk as such. This will be just basically straight up homotopy theory, simplicial homotopy theory. So given the format of this talk, I think I probably can allow myself to go into a little more details than I normally would in a seminar talk. And also given that the audience, I will not assume that the audience necessarily is intimately familiar with topics in simplicial homotopy theory, I will spend some time on a fairly basic introduction to this area before moving on to the constructive aspects, which are the main focus of this research that I'm presenting here. Well, and of course, if anything is unclear or you want me to explain something in more detail, please don't hesitate to ask questions during the talk. All right. So having said that, let's begin. So here's the classical theorem of Quillen, which says that the category of simplicial sets carries a proper and Cartesian model structure where weak equivalences are weak homotopy equivalences, fibrations are Kan-Fibrations, and cofibrations are the monomorphisms. This is a very old and classical theorem proven by Quillen in the 60s, at the same time when he introduced model categories in the first place. And since then, it became a foundational result in homotopy theory. A lot of what algebraic topologists and homotopy theorists do builds in many ways on this result. There have been many proofs of this theorem to date, but until very recently, none of them, none of the known proofs were constructive. So the question that I want to address here today is, can this theorem or some version of this theorem be proven constructively? And so the most of the theorems, most of the proofs of a theorem that you can find in topology books or in various papers are indeed widely non-constructive, and most of the time they actually rely very heavily on axiom of choice. Although to be fair, I think that the techniques that are necessary for this theorem have been known for quite a while. It's just that probably nobody really bothered to put them together into a complete proof. Just because topologists don't necessarily care about proving things constructively. But the axiom, removing of the axiom of choice from the argument is not such a big deal. But removing the excluded middle, that's something that requires a lot of work, and we will see how this exactly happens. So the motivations. Oh, sorry, too far. The motivations behind this, as I mentioned, is mainly study of models of homotopy type theory, and I will point you out to a reference about this a little later. But the other thing is the question of homotopy theory of simplicial sheaves, by which I mean, instead of the category of sets, take some other category, perhaps a Grothendieck topos, or maybe elementary topos, or maybe even some other type of category, and try to internalize this argument into this category and say something about simplicial, about homotopy theory of simplicial objects in that category. And doing this argument constructively is a very good first step towards results of this sort. And that's something that me and my collaborators are looking into. So both these topics are subject of ongoing research. And for this first one, I will give you some reference a little later. The second one has just started. There isn't anything published yet, but these are the things that we are thinking about. Okay, so as I said, I am going to start with some very basic, really very basic introduction to simplicial homotopy theory. And to begin with, I will present this theory from the classical standpoint. So I will talk about the theorem as stated here, and I will assume the classical logic for the first, I don't know, 15 or 20 minutes of the talk to give sort of an overview of basic results and not to get bogged down by the delicate issues that come up only when we are thinking about this constructively. And then later on, when I move to the constructive setting, I will point out how the things differ. In particular, in the first 15 minutes of the talk, I will say a couple of things that are not valid constructively. So be aware of that. I will later point out when this happened. Okay, so starting with the basic definitions. We have the category of simplices delta, which has objects that are totally ordered sets, non-empty sets, usually denoted by brackets M, containing numbers from 0 to M with natural order, and all order preserving maps between them. And we think those as sort of abstract simplices where these elements number vertices of some abstract simplex in dimension M. Morphisms of delta are called simplicial operators. And among them, we distinguish the injective ones that we call phase operators. And in particular, there are elementary phase operators, which are those denoted by delta I. They go from M-1 to M. And this delta I is a unique phase operator that omits I, meaning I is not in the image of this operator. And that, given that it is supposed to be injective and order preserving, uniquely describes this map. Now, a simplicial set is going to be appreciative over delta, so a contravariant functor from delta to set. Elements of xm will be called m-dimensional simplices of x, or m simplices of x for short. And the action of simplicial operators will describe how various simplices of x are attached to each other. And let me try to illustrate this fairly explicitly by looking at what happens in low dimensions. So the elements of x0 are going to be called the vertices or points of x. And the elements of x1 are called the edges of x. And let me get you familiar with this notation here. If we have an element x in x1, then this is an edge, so it is going to be denoted by an arrow like this. It has endpoints, two vertices, A and B. And these are denoted by notation A is equal to x delta 1. I am putting, this is maybe slightly non-standard, but I am putting simplicial operators on the right of the simplex that we're acting on because the action is contravariant, and I feel that this leads to more natural notation. So x delta 1 means the delta 1 phase of x, and x delta 0 means delta 0 phase of x. So those are A and B respectively. And maybe let me point out that here is this, at first perhaps odd reversal of indices in that the beginning is denoted by delta 1 and the endpoint is denoted by delta 0. That's simply because the index at delta denotes the vertex that we omitted. So then the one that remains is the other one. So when I'm saying delta 1, I'm actually zooming onto the 0 vertex and vice versa. In general, when I'm doing delta I in some higher dimension, what I'm saying is that I'm looking at the phase lying opposite of the vertex I. So it just omits this vertex. So for reference here, I drew the vertex, the simplex with label 0 and 1, so that you can see that when I'm applying delta 0, I'm omitting A, right? And then this goes on to higher dimensions. If I have a simplex U, then its phases are going to look as follows. There's going to be x, y, and z, one-dimensional faces. X lies opposite of the second vertex, z opposite of the first vertex, y opposite of zeroth vertex, and those have their faces themselves, which are vertices A, B, and C, and obviously they have to agree in various ways. For example, X and Z have to begin at the same vertex A, which is expressed by these identities here. And this of course goes on to higher dimensions. So in general, in a simplicial set X, you have some collection of these abstract simplices, each coming with the information of how it attaches to various other simplices via its faces, together encoding some sort of geometric homotopy theoretic structure. In addition to face operators, there are also degeneracy operators, which are the surjective ones. For the moment, I'm not going to speak about them. They will become very important later on when we get to the constructive part. So for the moment, and then I will say something more about degeneracy operators. Right now, I just want to mention that the category delta admits a presentation in terms of elementary face operators and elementary degeneracy operators, meaning really what this means for us that in order to specify a simplicial set, it's just enough to give these sets of simplices and the actions of these elementary face operators and also elementary degeneracy operators, which I haven't introduced for the moment, and verify that they satisfy certain identities, like the ones right here on the previous slide. So basically, what this is telling you is that in order to understand a simplicial set, you don't really need to worry about the action of all possible simplicial operators between all of these totally ordered sets. You just need to understand how a simplex in a particular dimension attaches to the one dimension lower, and then these relations tell you that everything is compatible all the way down. Then going forward, morphisms of simplicial sets are just morphisms of presheaves, and we call them simplicial maps. We have a category of simplicial sets. So the motivation behind this definition, well, originally it was a topological motivation. Basically, we think of these simplicial sets as modeling triangulated topological spaces. Very early in topology, people started realizing that many arguments, many homotopy theoretic arguments can be encoded in combinatorial ways, and triangulations were originally a standard technique of encoding those arguments, and this progressed more and more until the point where people realized that really, for the purpose of homotopy theory, you can make arguments purely combinatorial, and one way of making this precise is to introduce the category of simplicial sets and forget about topological spaces altogether and just work with that. And by the way, the Kan-Quillen model structure is one formalism which explains how to do this sort of in a consistent way. For type theorists, I could say that we can think of simplicial sets as interpretations of types, where we think of vertices as corresponding to elements of a type and edges as corresponding to elements of its identity type. And of course, higher simplices are supposed to in some ways correspond to elements of higher identity types on our type, but that correspondence is fairly complicated because the shapes of simplices are, they do not match up with the shapes that we get out of identity types. But what's on the slide, that's the correct way of thinking about this. And but as I mentioned, I'm not going to go into this direction. There are plenty of places to read about simplicial models of type theory. Okay, so let's introduce some. So we have set up the category. Let's introduce some notions in that category and build up some homotopy theoretic framework in there. So some notation. So delta M is going to be the representable simplicial set, which means that the k-simplices of delta M are simply all simplicial operators from K to M. So you can imagine that this is really the simplex delta M, where somehow this simplex is really exhibited by the element representing this simplicial set, i.e. the identity of M, and various other face correspond to the faces of this M-dimensional simplex. There's also a bunch of non-face operators, non-injective ones. Those are degeneracies of the top simplex of all these various faces. In particular, the one simplex serves as an interval object, and this allows us to define a notion of homotopy between simplicial maps. So if I have two like this, f and f prime going from x to y, then a homotopy is going to be a map from x cross delta 1 into y that restricts to f and f prime over 0 and 1 respectively, so over the endpoints of this one simplex. Alternatively, you can think about this as by an adjunction corresponding to a map from x to the internal home object y to the power of delta 1. So, at this point, I'm using all the basic facts about the category of precious that we're working here with. Namely, it has limits, it has colimits, it is Cartesian closed, so it has this internal homes. Okay, and having defined homotopies, we can define homotopy equivalences, and we're going to say that a map from x to y is a homotopy equivalence if there is a map going in the other direction from y to x, such that both composites are homotopic to the respective identities on x and on y. And this might be via zigzags of homotopies. So the relation of being connected by a homotopy is in general not an equivalence relation. So if I want to make this a reasonable notion, I would say that there might be a bunch of intermediate maps between the composite GF and identity of X that are connected by a sequence of homotopies possibly going in various directions. And so this is like the first approximation of the notion of homotopy equivalence that we would like to work with. And it is somehow directly lifted from the corresponding notion of homotopy equivalence in topological spaces. However, we quickly discover that that's not quite what we really want because of our issues with this definition. And let me illustrate this on some examples. So here, this is really not a big issue, but I'm putting this up as a sort of first step to the actual issue that will come up a little later. So we have this simplicial set that I'm calling the horn lambda 1, 2, and I will introduce the horns precisely in a moment, which consists just of these three vertices 0, 1, 2, and two edges connecting them like in the picture. So this is homotopy equivalent to a point, i.e. it is contractible, but it's not contractible via a single homotopy. We need at least two. So, I mean, if you unpack the definition, what the definition says is that we want to find a homotopy connecting the identity map on this simplicial set to some constant map on any of the vertices, 0, 1, or 2. Well, so we see that this cannot be connected by a single homotopy to 0, because such a homotopy would in particular include a direct path to every other simplex, in particular 2. And there is no direct path here. Similarly, we cannot contract in one step to 2 because there is no edge connecting 0 to 2, so for the same reason. But we also cannot contract in one step to 1 because the single contracting homotopy would need to have definite direction, but the edge is pointing from 0 and another one is pointing towards 2. So we cannot also put them in a single homotopy. But if we do it in 2 steps, then we can do it, no problem. We can include an intermediate map which maps this entire simplex, say, onto the edge 0, 1. So it is the identity on the edge 0, 1. It collapses 2 onto 1. And then in one step, we take a homotopy which connects identity to this intermediate morphism, and then another homotopy which connects it to, say, the constant map at 0, or something like this. So that's what happens, but this in itself is not such a big problem. But the same problem shows up in other examples. For example, let's say that we take a look at the spine of N. So the spine of N is a simplicial set that has natural numbers as vertices, and there's exactly one edge going between each pair of consecutive natural numbers. So this is not the nerve of n. The nerve of this poset of natural numbers would have many more edges and higher simplices. This has literally only this that's displayed on the slide, except that it goes to infinity. Oh, sorry, I went too far. So this one is in fact not homotopy equivalent to delta zero at all, because if I try to contract it to any point, then I cannot connect all other points to this chosen point by a homotopy of bounded length. I can connect any point to any other point by paths, but they will have arbitrary long. They will be arbitrarily long. On the other hand, this thing should be contractible, because I mean, if you think about this topologically, this basically corresponds just to half open interval, or I mean, just a half of a real line starting, say, from zero going to infinity, and that's contractible. So what I'm saying is that one downside of this combinatorial approach is that because we made everything very, very finite, like everything is described in terms of some finite operations, we lost track of some infinite structures that can often be equivalent to some finite structures, and our formalism doesn't capture this yet. So in order to fix this, we have to correct the definition of homotopy equivalence to weak homotopy equivalence. So I'm getting there, but first let me introduce these horns precisely. So the horn, denoted by lambda im, is going to be the simplicial subset of delta m, which is spanned by all the faces of delta m except for the identity, i.e. the top simplex, and the face delta I, so the one lying opposite of a vertex I. And what you see is, what you see is in dimension 2, lambda 0, 2, lambda 1, 2, delta 2, 2. All of those things are contractible, but via more than one homotopy. And then we are going to say that a simplicial set K is a Kan complex if it has the right lifting property with respect to all these horn inclusions. So whenever I map a horn into K, I can somehow extend it to the entire simplex. So basically what this is saying is, you see, these things are homotopy equivalences, but they do not admit retractions. Topologically speaking, if these were topological spaces, I could always retract a simplex back onto the horn, and that would say that in the category of topological spaces, every space would satisfy this lifting property. In simplicial sets, this doesn't always happen, so we are kind of distinguishing the class of Kan complexes. These are basically those simplicial sets that think that this map has a retraction. And this turns out to magically solve the issues that we discussed before. Namely, if I declare that a map F is a weak homotopy equivalence, when for all Kan complexes, the induced map between the mapping spaces like this is a homotopy equivalence, then this turns out to be a good definition, which, well, first of all, it solves problems like the one from a slide before. Things like the spine of N are now contractible in the sense of this definition, i.e. weakly homotopy equivalent to a point. And it solves all sorts of other issues that we might have with the notion of homotopy equivalence. This is all over a well-behaved class, better behaved class than the class of homotopy equivalences. And I should point out here that this is a place where the fact that this definition works, that relies on classical logic, and that's something that we'll have to carefully adjust when we go to constructive logic. Okay, so just to complete the set of our definitions, I'm going to say that a map is a confibration if it satisfies the same property that I have just used to define Kan complexes. Okay, so let me maybe just say that you might be familiar with other definitions of weak homotopy equivalences, say that's a simplicial map that becomes a homotopy equivalence upon geometric realization. So that turns out to be equivalent, at least classically. I have not looked at homotopy theory of topological spaces constructively, so I have no idea whether this would be a reasonable thing to do. I suspect that there would be issues with that. But in any case, I think that it is somehow conceptually more correct to have a combinatorial definition of weak homotopy equivalences if we are working with simplicial sets, and not refer to topological spaces if we can avoid this. Therefore, this is what I'm using, at least in classical logic. Okay, so just to build up to the formal statement of a theorem that I gave on the first slide, a weak factorization system on a category M is a pair of classes of morphisms L and R, so that every morphism factors as a morphism of L followed by a morphism of R, as in this diagram. And then the other two things say that morphisms of L and R have a lifting property with respect to each other. So whenever I have a square like this with a morphism of L on the left and the morphism of R on the right, then there is a diagonal map that makes both triangles commute. And moreover, L and R determine each other by this lifting property. So a thing is in R if and only if it has such a lifting property with respect to all things in L and vice versa. So that's what we call a weak factorization system. That's one thing that's needed in the definition of a model category. The other one is the 2 out of 3 property, which says that a class of morphisms W has this 2 out of 3 property if whenever I have two composable morphisms F and G, if any of the two FG over composite GF are in W, then so is the third one. Okay, so given that, we can define a model structure that's a triple of classes on a category M called weak equivalences, fibrations, and cofibrations. So that cofibrations and acyclic fibrations form a weak factorization system. Acyclic cofibrations and fibrations form another weak factorization systems, and weak equivalences satisfy the 2 out of 3 property. And here I'm using the standard terminology, which is that a cyclic cofibration means a cofibration that is also a weak equivalence, and similarly for fibrations. Sorry, I'm touching my scroll wheel while I'm trying to use the mouse. Okay, and given this definition, the statement of a theorem that I gave in the very beginning is now almost completely explained. I told you what the model structure is, what weak equivalences are, what fibrations are. Cofibrations are just monomorphisms. I have not explained what proper and Cartesian means, but that will come up later during the talk. So I want to say that this is not an obvious definition. So it's not the kind of structure that you encounter in a book. You look at the definition and you know exactly what this is for. This is a kind of definition which is it is cryptic. There's a lot of content hidden in there, but it's kind of encapsulated in this notion of a weak factorization system. It is not quite clear what it has to do with homotopy theory at the first glance, if you are not familiar with techniques of with how it is actually used. So along the way during the talk, I will point out some of those things, and hopefully this will clarify that for those of you who are not familiar with this already. Okay, so I think that this basically summarizes my intro to simplicial sets. So let's start talking about the constructive setting. So in the constructive Zenodo-Frankel set theory, which is what we are going to take as our constructive foundations, although the precise theory that we take for this is not so important, so I'm not going to really rely on any specific aspect of that. This is just to fix the context. We're going to have a very similar theorem, which says that the category of simplicial sets carries a proper Cartesian model structure where weak equivalences are the weak homotopy equivalences, fibrations are the Kan-Fibrations, and cofibrations are now something that I'm going to call really decidable inclusions. So there's an obvious difference in that I'm defining cofibrations differently. What's not apparent from the statement is that weak homotopy equivalences are also defined differently, and I will state this definition soon. Kan-Fibrations are defined pretty much in the same way as they were already, but constructively you have to be a little more careful about how you are thinking about this definition. Nonetheless, I would like to point out that I'm not really changing the definitions. what's happening here is that obviously when we move from classical logic to constructive logic, well, fewer things are true or provable, and therefore certain equivalences between notions are no longer valid. In particular, really decidable inclusions, whatever these things are, and I will define them soon, classically are exactly the same thing as monomorphisms. So classically, this model structure, this theorem reduces exactly to the theorem from the previous slide. It's just that you have to be more careful about how you choose between various constructive notions that might reduce to your classical notion that you used in the original theorem. Well, here are some references. So this theorem was first proven by Simon Henry, and then shortly thereafter, in collaboration with Nicola Gambino and Christian Sattler, we produced 2 more proofs of this theorem. And everything that I'm saying from this point on is joint work with Nicola and Christian, and this is also inspired by work of Simon. So there are 3 proofs out there. They rely on very similar ideas. They prove the same theorem, but they differ in the exact implementation of these ideas a lot as well. So in this argument, in this talk, I'm going to concentrate on one of those from our paper for definiteness. And this last paper by Nicola and Simon is something where they explore how this particular model category actually can be used to model homotopy type theory in a constructive way. And as I said, I'm not going to say much about this, so I'm saying to this paper to read up on what we talked about before.
Karol?
Oh, you're breaking, Karol. Karol?
We can't hear you, and your video is frozen.
Okay, so can you hear me now? I am getting some pop-ups saying that the internet connection is unstable. So have you lost much of what I've said, or
maybe 10 seconds?
How much have you said?
But since when?
I think last time we saw you, you were on the previous slide.
Yes. Do you remember what was the last thing that was intelligible?
You were talking about the last reference.
Oh,
yeah.
Okay. So about the last reference, I said only that in this paper, Nicola and Simon investigate how this constructive theorem can be used to provide a simplicial model of homotopy type theory, which was the main motivation behind proving the theorem in the first place. And I said that basically, if you want to know about this, try to read this paper. I'm not going to talk about this application in the talk. That's I believe what you missed in this last 10 seconds.
Okay, great.
All right. So having cleared that up, let me go on and start talking about constructive versions of some of the things that I mentioned so far. So first, let's talk about lifting properties. So if I have 2 maps, I'm going to denote by prob IP the set of all squares like this. So the set of all lifting problems between I and P. And I'm going to say that P has a right lifting property with respect to I if the map of all, if the map between that goes from the set of all simplicial maps from B to X to the set of problems has a section. So you see, if I have a map from B to X, this gives me a particular solution to a problem. And a section is just something that picks out solutions to every problem. But when I say that this is a section, now I am now emphasizing a constructive aspect of this, namely to say that a lift exists constructively is really to provide a prescription for how to construct this lift. So in particular, it will be convenient to think about this prescription simply as a function that for any such problem spits out a preferred solution to that problem. And a notion that's going to underlie everything here, that somehow complements what I have just said about sections, is a notion of a decidable inclusion. And that's a function between sets which has a complement. So such that there is some other set C, the complement of A, so that X is the coproduct of A and C, a disjoint union of A and C. So logically speaking, we are saying that the proposition X belongs to A is decidable. The excluded middle holds for this particular proposition. And I think what's in background here that I'm not going to really highlight very much is that decidable inclusions and split rejections form a weak factorization system on the category of sets. So in particular, what I'm saying here is that somehow this notion of a lifting property that I'm describing here is in a sense enriched over this factorization system in simplicial sets. And that's something that I'm not going to make very precise, but if you are more categorically inclined, that might be a helpful thing to keep in mind as we go along. Okay, so now let's revise some definitions. I'm going to say that a Kan-Fibration is a map with a right lifting property with respect to all Horn inclusions, as before. And I'm going to say that a trivial cofibration is a map with a left lifting property with respect to all Kan-Fibrations. So now constructively, of course, there's a bunch of existential quantifiers in this statement. And of course, constructively, the proof has to provide explicit witnesses for all these existential quantifiers. And maybe a good way of thinking about this is really these Kan-Fibrations are structured. In some sense, what we are thinking of is really a map together with a choice of a bunch of these sections of the maps from the previous slide, which witness that this map actually has this lifting property. And similarly, this works for these trivial cofibrations. And at this point, I should be explicit about the terminology that I'm using here. On the slide so far, I was talking about acyclic cofibrations. And let me remind you, acyclic cofibration is a cofibration that is also a weak equivalence. A trivial cofibration is just a map with this left lifting property. Part of a theorem saying that there is a model structure is that trivial cofibrations are exactly acyclic cofibrations.
All right.
So people.
What? Sorry. Okay, I guess I didn't have to do that since it happened.
Are the same.
Wait, Karol?
Am I breaking up? Can you hear me?
Yes. So the last thing I heard was a part of showing the theorem of the model structure is showing that acyclic cofibrations are trivial cofibrations, or maybe the other way around. I mean,
both ways.
They are the same.
Both ways. So I was just clarifying that usually people are using these notions interchangeably because they denote the same thing, but because the main point of what I'm doing here is to prove that they're actually the same, I'm being careful about labeling each definition by a different name before I actually prove that they are equivalent. Right. Okay. So then I have boundary of a simplex, which is just a simplex with a top simplex removed. So all the faces except for the top one denoted by identity. And that leads to another notion, namely that of trivial fibration, which has the right lifting property with respect to all boundary inclusions. And then a cofibration is something which has the left lifting property with respect to all of those. And somehow in talking about all of this, I sort of implicitly assumed that we have factorization systems. And indeed, these notions form two weak factorization systems, and that follows from the constructive version of a small object argument. So let me discuss that next. So here's the theorem. It is nearly identical to a classical theorem about the small object argument, with one difference. It just says that if I have a set I of maps between finite simplicial sets, each of which is a level-wise decidable inclusion in the sense of a definition from a couple of slides before, then there is a weak factorization system where a morphism in the right class, the morphisms in the right class are exactly the ones that have the right lifting property with respect to this original set I. And the proof of that, and this is the first place where we are actually starting to distinguish between classical and constructive arguments. Let me tell you how this goes. So at the first glance, it is very similar to the classical small object argument. I start with some map. I'm going to call it P0 going from x0 to y in anticipation of the induction that I'm doing here. And I'm iteratively adjoining all solutions to the lifting problems that I have at a given stage. If I started with P0 here, I'm going to take all the lifting problems between all little I in my set I into P0, and I'm going to take a push out of all of those to produce X1. And here I will obtain P1, and I'm going to go on, and I will do it countably many times. I will take a colimit at the stage of omega, and this is going to be my X infinity. This will provide me with two maps, x0 to x infinity and to y, which is going to factor my original map. And it is fairly obvious that this first map is in L. That's because it was obtained by sort of standard operations like coproduct and pushout, and those preserve left lifting properties. And then to show that the other one is in R, this is where classical argument breaks down a little bit, and we need some extra assumption, namely this of level-wise decidability. And okay, so the point is that if you are trying to solve a lifting problem against this, you are going to have a map from a domain of something in I into X infinity. You would like to say that this map factors through some stage. But the point is that you actually are trying, think about it like this. You're trying to provide a structure of a map in R on this thing. So you actually need to explicitly say which map, which lift you are going to produce for any particular lifting problem. So if you are saying that the map factors through some stage, you need to identify this stage explicitly. So a natural idea would be to say, for example, let's take the minimal number, natural number k, such that my lifting problem factors through xk, and that works. The problem is that constructively, not every inhabited subset of natural numbers necessarily has a minimum. It happens for decidable ones, and it turns out that the assumption that the maps in I that I started with are level-wise decidable is enough to conclude this. So we have to be a little bit more careful, but at least for the kinds of factorization system that we are trying to produce, a small adjustment of small object argument works. And somehow this highlights how we are approaching this entire project, in that, you know, we would really like to use excluded middle because it is useful. So we just sort of we are just assuming it locally by inserting these level-wise decidable inclusions where we need them, and then we have some limited form of excluded middle at our disposal. But then in the end, it turns out that all these level-wise decidable, all these decidable inclusions can be constructed, and you know, I don't actually need to assume any excluded middle globally, so to speak. All right. Okay, so now let me unravel some of these definitions and give you some characterizations of these notions that I have just introduced. So one thing that happens now is that these cofibrations are constructively, they are monomorphisms, but constructively not every monomorphism is going to be a cofibration. In particular, not every object is going to be cofibrant, not necessarily. I mean, of course, everything is consistent with classical logic, so it could happen that everything is cofibrant, but it's not provable that everything is cofibrant. So a simplicial set is cofibrant if and only if for all degeneracy operators, the map induced by a degeneracy operator is a decidable inclusion. So it is a decidable proposition if a given simplex is of a form U sigma for some operator sigma. And here's some example. For example, degeneracies of a one-dimensional simplices in one dimension higher, they basically duplicate one of the simplices. They either duplicate this vertex A, or they duplicate this vertex B. And these are two possible degeneracy operators that can act on a one simplex. So basically what I'm saying is that among all simplices in A2, it is decidable whether a simplex is of this form, and it is also decidable whether a simplex is of this form. That's what it means to be cofibrant. And equivalently, I could also say that it is decidable whether a simplex is degenerate by some degeneracy operator, not necessarily a fixed one. And that's encoded by this notion of a latching object. So the latching object in this context is just going to be a subset of all degenerate M simplices of X. So if you are familiar with the notion of a relied cofibration, you are kind of seeing that what I'm doing is lifting this factorization system of decidable inclusions and split rejections on set to a relied factorization system on simplicial sets. That's what's happening in the background. And indeed, it is also true that a map is a cofibration if and only if this sort of relative thing is a decidable inclusion. So the proposition a simplex is degenerate or in the image of a subset, that proposition is supposed to be decidable. And that's, again, equivalent to really decidable inclusion. So the same thing, but degenerate in the abstract, not necessarily with respect to a particular degeneracy operator. Okay. So these cofibrations and trivial cofibrations that we have thus produced satisfy a bunch of useful properties. For example, we satisfy the push-out product property, which says that if I have two cofibrations, then this map, which is like the union of these two products, is a cofibration, and it is trivial if one of those was trivial. This is, by the way, a part of what I meant. I mean, this is exactly what I meant by Cartesian in the statement of a theorem of a main theorem. This basically says that the products are well behaved and that exponentials are well behaved. So the proof of this, the standard classical proof, turns out to be constructive because this is just some explicit combinatorics of horns and boundaries. I'm not going to go into that. Let me just note some consequences about exponentiation. We have things like if A is cofibrant and I have a fibration or a trivial fibration, then this induced map on exponentials is a trivial fibration. And dually, if I have a cofibration, which is perhaps trivial, then if I home into a Kan complex, then I get a fibration, which is trivial if that one was. And crucially, if A is cofibrant and K is a Kan complex, then this exponential is a Kan complex. Classically, all of this would be valid without the assumption of cofibrancy because everything was cofibrant classically. So somehow the big part of why this is difficult is because instead statements like this, we have to worry about some of properties of those. Let's go to weak homotopy equivalences because this is the crucial part.
Hang on, sorry, we lost you at part of the reason why it's difficult.
Oh,
and
so
it was so difficult that it just broke the sound.
So the reason why the constructive version of the theorem is difficult is because we need to worry about the assumption of cofibrancy. All these statements classically would be valid without this assumption, simply because this assumption is vacuous, everything is cofibrant. And the arguments become difficult because whenever I want to apply one of those, I have to worry about verifying that something is cofibrant. Okay, so let's now talk about weak homotopy equivalences because we discussed fibrations and cofibrations, and weak homotopy equivalences actually was crucial. Now, the definition mimics the one in the classical setting that I gave in the beginning of the talk, but it is somewhat more complicated because I have to worry about cofibrant objects now. So I'm going to start by saying that a strong cofibrant replacement of a simplicial set is another simplicial set X tilde, which comes with a trivial fibration like this. So that's something that you can always produce via the small object argument that I have discussed. And then the definition of a weak homotopy equivalence is going to come in 4 stages, successively generalizing it to broader and broader context. Previously, you can think about this in a similar way. We had a definition in 2 stages. I first said this is a homotopy equivalence for Kan complexes, and then there was a general definition for everything. I will have to take it slower because of cofibrancy right now. So first, I'm going to say if X and Y are cofibrant Kan complexes, then a weak homotopy equivalence is just a homotopy equivalence as defined before. So it has inverse up to homotopy. If X and Y are Kan complexes but not necessarily cofibrant, I'm going to say that this map is a weak homotopy equivalence if it has a strong cofibrant replacement in this sense, that is a weak equivalence in the sense of a previous case. And then I'm generalizing further. If X and Y are cofibrant, then I'm going to say that this map is a weak homotopy equivalence if it becomes a weak homotopy equivalence in the sense of a previous proposition, in the sense of a previous definition, whenever I map into every Kan complex K. And note that this makes sense because I'm assuming that these things are cofibrant and this is a Kan complex. So I'm already using the result from the previous slide, even in order to make sense of this definition. And then finally, I'm sort of repeating the second case by saying that for arbitrary X and Y, a map is a weak homotopy equivalence if it has a strong cofibrant replacement, but is a weak homotopy equivalence in the sense of a third definition. So there is like a successive sequence of 4 definitions that make it, that expand it to wider and wider class of simplicial sets. I don't find this very satisfying, but that's basically the best that I can do. I'm now realizing that I'm going actually really slow compared to what I anticipated.
You started a few minutes late, so feel free to.
Okay, I mean,
how much time do you need to finish?
I don't know, but it might be like another 20 or 25 minutes. I don't know if that's.
Let's try to keep it under 20 for sure, so that we have time for questions.
I mean, I definitely don't want to stretch it too far, but I mean, I was hoping that I will be able to say more. So I will have to speed up. Okay, so then I'm going to mention that there's this notion called 2 out of 6, which is a generalization of 2 out of 3. If I have 3 maps, then if the composite of these 2 is a weak homotopy equivalence and of these 2 is a weak homotopy equivalence, then all of these 3 and the composite is also a weak homotopy equivalence. This is a bit of in the context of model categories, this actually follows from 2 out of 3, but in general it does not, and it is useful to verify it first. And the reason why I'm doing this is because as an intermediate step towards the proof of a model category axioms, I'm going to use something called a fibration category. So I'm going to show that the category of Kan complexes is a fibration category, and it means that it satisfies the following axioms. It has a terminal object and all objects are fibrant. Pullbacks along fibrations exist, and fibrations are stable under pullback, and also acyclic fibrations are stable under pullback. Every morphism factors is a weak equivalence followed by fibration. Weak equivalence satisfy 2 out of 6, and here there are 2 more axioms similar to the one about. Is there an issue? Am I breaking up again?
Yeah. So weak equivalence is satisfied 2 out of 6, and here.
And the other 2 axioms, the remaining 2 axioms, are just very similar to the second axiom. They just talk about some other limits, about stability of acyclic fibrations and fibrations under some other types of limits. So these are axioms that are weaker than the axioms of a model category. They follow from the axioms of a model category, and they are easier to establish, and they are a convenient intermediate point in the verification of the axioms of a model category. So let me quickly go through the proof of this. So first of all, there is a cancellation for trivial fibrations, which says that if I have two maps such that P and QP are trivial fibrations, then so is Q. Given that, that's a very easy lemma, we can show that a Kan fibration between Kan complexes is acyclic if and only if it is trivial. So it is characterized by a lifting property. And this is going to, in particular, imply that acyclic fibrations are closed under pullback. So very quickly, the idea is that if we could assume that X and Y are cofibrant, then acyclic means there is a homotopy inverse, and using various lifting properties that follow from the push-out product property, I can strictify the homotopy inverse to something called a deformation section. So a map which is a section of P, and such that the other composite is homotopic to identity sort of fiberwise over Y. And then by composing with that, I can basically solve arbitrary lifting problem against boundary inclusion. I mean, this involves some more steps, but I'm being brief here. And then, if I want to go to general Kan complexes that are not necessarily cofibrant, I use the previous lemma because the definition was that this is a weak equivalence if it has a strong fibrant replacement that is a weak equivalence. So if I have proven theorem here for cofibrant things, then by cancellation, this is going to be trivial as well. Okay, and that is, so this basically gives you the only difficult thing in the proof of a theorem about the fibration category. All the other stuff we have already verified in the meantime, or it's rather easy. Okay, and really the reason for doing that was to immediately dualize, to say that the category of cofibrant simplicial set is a cofibration category, i.e. it satisfies all the dual axioms, and the critical one of those is that pushouts along cofibrations, that pushouts of acyclic cofibrations are acyclic. That's really the crucial thing. And this is actually quite trivial because of how we set up the definition of weak homotopy equivalence. This just reduces to the previous theorem sort of by duality, by simply applying this Hom factor into all Kan complexes. Because these pushouts got turned into pullbacks and we apply the previous thing. So notice that in the previous theorem, we established a lifting property of acyclic fibrations, at least between Kan complexes. Right now, we have proven this theorem without establishing any lifting property of acyclic cofibrations at all. We kind of abstractly just know that they have some closure properties. So we are still quite far away from proving the actual theorem about a model structure, but, sorry, I skipped ahead. But we are getting very slowly. Too slowly, unfortunately. Okay, so let's move on. So one upshot of things like having a cofibration category is that we can prove lemmas like this. There's a gluing lemma, which basically says pushouts along cofibrations are homotopy pushouts. So if I have a cube like this, where both the top and bottom faces are pushouts along cofibrations, then if the three vertical maps are weak equivalences, then the fourth one, the one induced on pushouts, is also weak equivalence. This tells us that pushouts along cofibrations are weakly equivalent, are a homotopy invariant. And the statements like this are really the reasons why we care about model categories and why we care about cofibrations and fibration categories, because these are the frameworks that allow us to prove statements like this. And right now, we have proven this for maps between cofibrant objects. The assumption is that all of this is cofibrant here. But that's a good starting point to proving more things that we need. Okay, so very quickly, let me say something about bisimplicial sets. So these are presheets over delta cross delta, or simplicial objects in simplicial sets. And well, let me start skipping stuff. So there is a notion of cofibrancy, which is similar and built in the same way as the notion of cofibrancy that we discussed for simplicial sets. Every bisimplicial set has a diagonal, which is just exactly what you expect. And bisimplicial sets also have skeleta. So basically these are sort of, so the skeleton is something given with respect to a particular direction, either one or the other, and it's basically somehow generated by sub-objects of k-dimensional simplices. Here's a formula in terms of a Kan extension. One upshot of the gluing lemma and the category, the cofibration category that we have, is that we can prove the following classical fact. A map between cofibrant bisimplicial sets, which is level-wise weak homotopy equivalence induces a weak homotopy equivalence on diagonals. And that's a very classical theorem used all the time in simplicial homotopy theory. It is valid here, except that you have to assume that everything is cofibrant. And the proof of this is kind of, just, I'm not going to go through this diagram in detail because I don't have that much time, but basically you decompose the problem into multiple applications of a gluing lemma that we know that we have from the previous slide, and we can decompose this problem because we assume that things are cofibrant. The cofibrancy gives us this decomposition, but we can apply the gluing lemma over, and the conclusion follows nicely. And okay, so why do we need that? Because we're going to talk about the barycentric subdivision. So the barycentric subdivision of a poset is a poset of non-empty subsets. Well, actually, just of a totally ordered set is the poset of non-empty subsets of this totally ordered set M, and we can subdivide any simplicial set sort of just by taking every simplex in this simplicial set, subdividing it, and reassembling them together again via this colimit. And for example, the picture for lambda 2 for delta 2 looks like this. That's what you would think of as a barycentric subdivision. So you basically replace every simplex in your simplicial set by a picture like this. And there's an order preserving map which takes every subset to its maximum, and that induces a natural transformation from subdivision back to original set X. This allows us to define the classical functor X, which is just the right adjoint to the subdivision, and the X infinity, which is the colimit of iterations of X along the map, which is adjoint to this maximum map from the previous slide. This has some properties which are listed here. X infinity preserves finite limits, Kan-Fibrations between cofibrant objects, and for cofibrant things, it is a Kan complex, and the comparison map that you obtain from this is a weak homotopy equivalence. So it is a fibrant replacement functor on cofibrant objects. So these statements 2 and 3, I'm not going to go, I intended to, but I'm not going to go into explanation of why the cofibrancy assumption is necessary here, but that's basically for the same reason as in the small object argument. We need to know that when things factor through some stage in this colimit, we can identify the stage where they factor actually. And then in order to show that this is a weak homotopy equivalence, we use a nice argument of Latch, Thomason, and Wilson, which relies on this diagonal lemma that I have just described. And this is a really cool argument, but I think that I don't really have that much time to go into detail. So let me just very quickly say that we can write down a clever square of bisimplicial sets, which looks like this. And then we can apply the diagonal lemma 3 times in 2 different directions. So we can fix M and obtain something like this. And we're going to see an honest homotopy equivalence here because it is induced by some honest homotopy equivalence between these exponents. And if we fix the other direction, we're going to have homotopy equivalences in this other way. And then this means that these 3 maps, this one, and this one, on diagonals induce weak homotopy equivalences. And therefore, by 2 out of 3 in this diagram, I obtained that my map is a weak homotopy equivalence. So I know that this was very quick, but this is a really clever argument. It's worth, for the first half of...
oh, wait, sorry.
Yes?
It's very quick, but it's a very cool arg. I suspect it was a very cool argument. Well, it was a very cool argument, but I don't know if that's what you were trying to say.
I just said that that's something that I would recommend studying if you are interested, because that's like a little gem of simplicial homotopy theory in my opinion. And I regret that I had to go through it so fast. Okay, so now we are ready for the first half of a proof of a main theorem, namely that a fibration is trivial if and only if it is acyclic. That's one of the two things that we have to prove. The other one is that the same holds for cofibrations. So the proposition is that these two things are equivalent, and an intermediate fact is that P has contractible fibers. So first of all, we can assume that X and Y are both cofibrant because of a cancellation lemma that came up a couple of slides ago. And then implication from trivial to a cyclic is straightforward, so I'm going to skip that. If something has contractible fibers, then basically, if I want to solve a lifting problem against such a thing, that I can kind of squish this problem, contract it into a fiber, solve this in a fiber, which I can do because I assumed that I have a contractible Kan complex here, and then can kind of uncontract this solution to the solution of the original problem. That's very, very explicit and constructive. And then the final step from acyclic to contractible fibers uses X infinity, and this is the place where we actually need to use cofibrancy. So basically we take this fibration, which is acyclic, and we would like to show that it has contractible fibers. So we take this pullback square in the back, which has a fiber here. We apply X infinity, and now we land it in Kan complexes where we know that acyclic fibration has contractible fibers because this was basically an axiom of a fibration category that we have verified. So by using properties of X infinity, we can go back and conclude this for our original square. And that basically finishes off the one half of a proof of a theorem, namely that trivial fibrations coincide with acyclic fibrations. The remaining part is to verify that trivial cofibrations coincide with acyclic cofibrations. And this is, the thing is that once you get this far, the second part is normally trivial. Because, I mean, if you have any experience with constructing model structures, you usually know that it is hard to prove one of these two statements. But once you have this, there is an easy trick to prove the other one. Unfortunately, this easy trick has an assumption which is difficult to verify in our setting because of not everything being cofibrant. So I do have slides that explain this, but maybe at this point, this would be a good point to decide how much longer I should go for, or whether I should go any longer at all. Chris, what do you think?
I suggest the following, maybe.
So actually, yeah.
Okay.
Well, I mean, I'm looking at, by my count, I have 5 slides left. So, I mean, I could go through all of them quickly. That's one thing that I could do.
I was going to suggest that we're going to do a quick round of applause, and then we're going to see if there are questions. And if there are no questions, then there is a standing question of finishing this.
Okay, fair enough.
This talk. So, okay, so I'll remind everyone that what we're doing is silent applause, meaning we're not unmuting microphones, but we're clapping nonetheless. So there we go. Thanks, Karol.
Thank you.
And if you can see us, yeah, everyone's clapping. All right. And at this point, I'm going to ask, are there any questions? If anyone wants to ask a question, please just unmute your microphone and ask the question. There's also the chat. If you, for some reason, cannot unmute your microphone, you can write your question in the chat. And at some point, I should shut up and let Karol finish the talk, unless there are questions.
Okay, so actually, if people are asking questions in the chat, could you please monitor that for me? Because I'm not that...
I will monitor it closely, yes.
Okay, thank you. I'm not that familiar
with all over the chat, yes. Okay.
I have a question I could ask.
Go for it.
So, and I don't know what's on your remaining slides, so maybe you address some of these things, but I'm curious how this compares to other work on trying to do a constructive model of simplicial sets, like Benno has done work on that. Can you say something about that, or maybe Benno can comment?
Well, not really. So I'm not that familiar with Benno's work, but I believe that this is based on his joint work with Richard Garner, that uses some sort of Moore homotopy theory and structure fibration different type. So I'm not familiar with that enough to really say, but my impression is that it is quite different. It appears to me to be different, and I cannot quite say what the actual relationship is. But
I don't want to put you on the spot, but
maybe what I'm trying to say is that I believe that his notion of vibration is different than ours. But I have no confidence in that statement.
Yes. So can people hear me or?
yeah.
Yes.
Yeah. So I think, so we're basically following quite different approaches, I think. So what you're saying is that, basically you're staying very close to the classical definitions of a countervibration and a trivial vibration. And yeah, we're trying to do something more in the cubical spirit, where we try to add uniformity conditions to our lifts. So again, the hope is that that sort of classically these things are equivalent, but in our case that is not so obvious as in this case. And another big difference, of course, is that, well, you seem to have finished constructing the model structure, and for us, this is still work in progress. So,
I see.
Thank you, both of you.
All right. Are there any other questions? Does this theorem generalize to simplicial pre-sheaves? And it's not Rick asking this question.
Simplicial pre-sheaves. Well, so I could understand this question in a couple of different ways. So, but the way I'm choosing to understand it right now is that, well, this is basically part of work in progress that I put on one of early slides, where we are trying to do, in fact, something more general. So generalize it not just to simplicial pre-sheaves, but to simplicial objects in an arbitrary topos. And I believe that, we have been working on that recently. Well, at the moment, I am quite confident that this model structure that we have here has pretty much direct counterpart for simplicial objects in a Grothendieck topos. The argument is very similar, but it requires a couple of adjustments to work internally in a Grothendieck topos. So that, of course, captures the case of simplicial pre-sheaves in particular. But we have reasons to believe that we can go further to something like perhaps elementary topos with natural numbers object or something along these lines. But that remains to be investigated.
Valerie, does that answer your question? I'm assuming it's Valerie Isaev. It just says Isaev, but yes, it answers his. Okay. Any other questions?
Yeah. Hi. Can you hear me?
Yes.
Yeah. So kind of just to follow up on that question, do you know how the model structure on simplicial pre-sheaves, for example, would compare to the more usual notions like injective or projective model structures?
So we have strong reasons to believe that it is different.
Yeah, I would also guess that. Yeah.
And like investigating what it is exactly is part of our project. And so in this, Simon Henry is also involved in this particular project. And actually, I would suggest asking him really, because I think that he's ahead of us on this particular question. And he has a specific conjecture saying that the infinity category presented by this model structure would be some kind of exact completion of sort of corresponding topos, corresponding infinity topos that, like, yeah. What I'm trying to say is that you can sort of take the free infinity topos. What you obtain is not quite that free topos, but some kind of exact completion of the topos. And well, okay, let me put it like this. This is how much I understood from a conversation that I had with Simon on this topic. So please don't put it on him if I misrepresented that statement. But it is something along these lines. It is not something obvious.
Would it be hypercompletion?
Excuse me?
Hypercompletion, maybe?
So I'm afraid that I don't remember off the top of my head. It is some kind of exact completion.
Okay.
There's another question.
Yeah, I mean, we have not proved that. That's conjectured.
Okay, thank you.
There's another question in the chat. Can this construction be carried out internally in the topos of simplicial sets in the spirit of Orton pits?
Well, I don't know. So as I have just said in the answer to one of the previous questions, it can be carried out internally in any Grothendieck topos, but I'm not sure how this compares to the spirit of Orton pits, because
how does it compare to Orton pits without the spirit?
Okay. Yes, I'm afraid that I'm not familiar with that work well enough to really say how it compares.
All right. Is there a follow-up to this, or okay? We'll entertain more questions, maybe. It seems like, yeah. Okay, I see no follow-up on chat. I hear no follow-up in the open, so I guess maybe 5 minutes to finish 5 slides.
If that's what you recommend,
that's perfect. Yeah. Okay.
Okay. So let me let me pick up where I stopped. As I said, we have verified that trivial fibrations coincide with acyclic fibrations. Now we would like to say the same for cofibrations, and that gets a little hairy because not everything is cofibrant. So one thing that we are going to use for this is another little bit of classical simplicial homotopy theory, namely Quillen's theorem A, which says that if we have a functor between two categories, then we have a criterion for when it induces a weak homotopy equivalence on the nerves, and namely the criterion says that the nerve of every slice over every object has to be weakly contractible. And that works just as in the classical setting, except that we need to insert an assumption that this category has decidable identities. So basically think about the category as a category internal to sets. You have a set of objects and a set of morphisms, and you have a map which maps every object into its identity morphism, but has to be a decidable inclusion. So it is decidable if a morphism is identity or not. And this theorem has a proof which is, I'm not going to go in detail through that, but that's basically the exact same proof that Quillen used. It's just that we need to insert this extra cofibrancy assumption, but it uses the diagonal lemma from the couple slides before, and it works just fine. And with that, we can construct an explicit cofibrant replacement functor, which is given by the nerve of the category of simplices of a simplicial set X. So this is the category of elements of a presheaf. And this turns out to satisfy the exact dual properties of the X infinity functor, except that without the cofibrancy assumptions. So I did have some sketch of a proof here that maybe I'm going to skip, but somehow the critical yes, I don't think that I'm going to go into the details, but the critical step is on this next slide, and that's just many applications of the theorem A, basically. That's what it boils down to. But the upshot is that we do have a cofibrant replacement functor with nice properties exactly dual to the properties of X infinity. And with that, we can show that the cofibration is acyclic if and only if it is trivial. And the point being that usually it is obvious that trivial implies acyclic. Now it is only obvious for maps between cofibrant objects. That's because the definition basically just boils down to coming into a Kan complex, product properties, this ends up being a trivial fibration and everything is fine. But in general, the definition was more complicated, and without going into too many details, you can reduce from the general case to the cofibrant case by applying this cofibrant replacement functor, thanks to its nice properties. Like this square here, I mean, this was intended to come with a longer commentary that I don't have time for, but like this gives you this leaves you with an impression that there is just one sentence to be said here, but very small. So just wanted to say that. But T allows you to reduce the general case to the cofibrant case, and then you can apply the classical retroact argument. So if you have a cyclic cofibration, you factor it for a trivial one and a fibration, and then because you already know that this fibration, which is acyclic by 2 out of 3, is also trivial, you can lift and show that your original cofibration is a retract of this trivial one, and therefore is trivial itself. And this is an argument that always works, and this is the reason why whenever you need to construct a model structure, it is enough to show that trivial fibrations agree with acyclic fibrations and the other half follows. But the point is that in order for this to follow easily, you need to know this statement, which is normally obvious, but in our case, it required a detour via theorem A and so on. So this is actually my penultimate slide, but maybe let me not flip to the last one. Let me just say one sentence that the final slide contained the proof of properness of this model structure. But basically, once you have X infinity functor with its nice properties, this gives you right properness. And once you have this nice cofibrant replacement functor T with its dual properties, this gives you left properness. So I think that I can conclude here. Thank you.
All right, thanks. So before we move to the second round of applause, let me ask if there are any further questions. Especially, we have we have slightly less than 3 minutes, maybe 2 minutes for questions. So one question or something is within reason. Okay. I see or hear no further questions. So let's thank Karol again for this great talk.
Yep. Thank you everyone for attending.
And okay, before we're done, I'm just going to say the spring break is coming up. So Hottest will be on spring break. Dan and I are going to Florida to party with all the teenagers. So there will be no Hottest on March 5th, but we'll return on March 19th with John Sterling speaking. So unfortunately, next 4 weeks, if you're really committed to Hottest, it will be a little bit dry, but yeah. Okay, thanks everyone, and see you in 4 weeks.